Welcome to the 15th lecture of my series on thermodynamics. In the last lecture, we met the Clausius inequality, which says that if a cycle absorbs heats Q1, Q2, Q3 at temperatures T1, T2, T3, etc., then the sum over the entire cycle of Qn by Tn must be less than or equal to 0. If instead of taking heats at discrete values of temperatures, the engine absorbed heat at a continuum of temperatures, which is more common, the sum here gets replaced by an integral over an entire cycle of d cross q by t. And the Clausius inequality says that this has to be less than or equal to 0. Now, if this cycle had been a reversible one, then its reverse would also be an eligible cycle for which also Clausius inequality would be applicable. So, the cyclic sum of Qn by Tn would have to be less than or equal to 0. But in addition to that, the cyclic sum of minus Qn by Tn, the appropriate quantity for the reversed version of the cycle, must also be less than or equal to 0. And therefore, for a reversible cycle, this cyclic sum of Qn by Tn, the sum over the entire cycle that is, must be equal to 0. And its continuum version is simply that the integral of d cross q by t carried out over a complete cycle, provided that this is done under reversible conditions, is 0. Now, an immediate consequence of this fact that d cross q reversible by t over any complete path is 0 is simply the fact that if you were to go from a state I to a state f along two different paths gamma 1 and gamma 2, the integral of d cross q reversible by t carried out over path gamma 1 will be the same as that carried out over path gamma 2. And as we mentioned at the end of the last lecture, this is actually the stepping stone towards the definition of a thermodynamic quantity of great importance called the entropy. Now, let me just remind you of a very similar situation that we had involving the internal energy. Work done under general conditions was path dependent. However, experiments told us that adiabatic work done is path independent. And this is how we use the fact to define the internal energy of a state P. We chose an arbitrary state P0 as a reference state, and we calculated the work done to take you from P0 to P along adiabatic conditions and put a negative sign in front of that. Ended up with the internal energy which depends only on the state P and not on the path which you took from P0 to P. This of course is because adiabatic work done is path independent. And an immediate consequence of that turned out to be that the internal energy difference between two states, P and Q, is simply the negative of the adiabatic work done to go from P to Q. Now, a very similar situation happens with heat absorbed. Well, similar but slightly different. The heat absorbed integral of d cross q from I to f carried out along a path gamma depends on the path gamma. And that is of course signified by the fact that we call the differential d cross q instead of dq. D cross is meant to signify the fact that there is no function q whose differential this is. Well, d cross q divided by t is also in general something whose integral is path dependent. And therefore d cross q by t is also not an exact differential. On the other hand, just like adiabatic work done is path independent, d cross q by t carried out under reversible conditions is independent of the path, depends only on the initial state and the final state. This is exactly what Clausius inequality tells us. And now we can follow a procedure exactly identical to the one that we followed when we defined the internal energy to define a new thermodynamic quantity called the entropy. For this, just as we did for internal energy, we will choose a specific state P0. This state, as of now, is chosen arbitrarily. Now define a function of a state P. This function we will denote by S of P as simply the integral of d cross q under reversible conditions divided by t, and this integral is carried out from P0 to P. Along which path? It doesn't matter. Take any path from P0 to P and calculate this integral of d cross q reversible by t. Clausius inequality has just told us that this quantity is going to be independent of the path taken, so it will only depend on the point P, this point in state space, which of course is a state of the thermodynamic system. And of course it will depend on the state P0 that we have chosen, but P0 is fixed once and for all, so it shouldn't really matter. Now an immediate consequence of this is, if we have a path which goes from P to Q, and let's say this process is reversible, then the integral of d cross q reversible by t along this path from P to Q, along this magenta path here, can be calculated using the S value in a very simple fashion. Since the integral of d cross q reversible by t is path independent, the integral from P to Q is going to be the same as the integral along its path from P to P0 and then from P0 to Q. Of course, the integral now splits into two pieces, the integral from P to P0 and the integral from P0 to Q. Now the integral from P to P0 is simply nothing but the negative of the integral of d cross q reversible by t from P0 to P, and therefore it's minus S of P. And this thing is nothing but S of Q by definition. So we find that the integral from P to Q along any reversible path is going to be SQ minus SP, which is nothing but the increase in this quantity S along this path. This quantity, of course, is what we call the entropy. And so, notice that entropy in thermodynamics, in classical thermodynamics, is really not very different from internal energy. Internal energy in classical thermodynamics follows from the fact that work done under adiabatic conditions is path independent. Entropy in classical thermodynamics follows from a very similar fact. The fact that the integral of d cross q reversible over temperature is path independent. The infinitesimal version of this statement would be ds is equal to d cross q reversible by t. And that can be thought of as simply a statement of the fact, although d cross q is not an exact differential, not even under reversible conditions, but under reversible conditions, d cross q has an integrating factor, a function of the state or a function of the variables which describe the state, multiplication by which renders it into an exact differential. This integrating factor, of course, is nothing but 1 divided by the absolute temperature T. So what we see is that the Clausius inequality, when you restrict it to the reversible case, implies that a new thermodynamic quantity must exist. A quantity which is a function of the state and the state alone, a so-called state function, and you call it, of course, the entropy. Now, the Clausius inequality also works for irreversible cases. So it does actually say something about entropy, something more about entropy, that is, other than its mere existence. The fact that it allows entropy to exist is in itself a big thing, but the significance of the Clausius inequality does not end there. To see what the true significance of this entropy is, let us now consider a process in which some adiabatic path is used, not necessarily a reversible one, to carry a system from an initial state I to a final state F. After this process is completed, we go back to the initial state I by following some path which is reversible. Note that the adiabatic path may or may not be reversible, we do not know that from the beginning, and the reversible path has no guarantee of being adiabatic at all. But note that if you take both of these paths in succession, the adiabatic followed by the reversible one, you do end up with a cyclic process where the state of the system starts at I and ends up after the entire process back at I. So, because this is a cyclic process, the Clausius inequality works for this. If you were to integrate d cross q by t for this entire loop, you will get something which is less than or equal to 0. Now, of course, this integral over the entire loop is nothing but a sum over the adiabatic path from I to f, and then the sum from f to I along whatever reversible path you have chosen. So you get d cross q by t, I to f along this adiabatic path, and f to I integral of d cross q reversible by t. Note that in this part I have not mentioned what the path is. Of course, the path is this particular reversible path taken, but it does not matter because we have already seen that for the integral of d cross q under reversible conditions by the absolute temperature, the path is not important. This integral will depend only on the initial and the final states of this. Now, d cross q for the adiabatic part of the path is simply 0, and so is d cross q by t. So this integral simply drops out. This integral, on the other hand, is something we have already seen is related to the entropy. It's actually going to be Si minus Sf. Note that the final state for this reversible process is actually our initial state I, and the initial state is F. So the increase in entropy, which is the integral along this path, is nothing but Si minus Sf. And this part just gives you 0. So for this complete cyclic process, d cross q by t's integral for the closed cycle turns out to be simply Si minus Sf. But Clausius inequality has told us that this has to be less than or equal to 0. In other words, Sf must be bigger than or equal to Si. This is a very, very important statement which says that if you carry out an adiabatic process on a system, its entropy will never decrease. When a system is isolated from the surroundings, any process carried out on it has to be adiabatic. So another way to talk about this would be entropy never decreases in an isolated system. So now we are in a position to state the second law of thermodynamics using the language of entropy. A state function called entropy exists. That's one part of Clausius inequality, and it never decreases for an isolated system. That's the second part. Even if the system is not isolated, then the system and the surroundings taken together, which we usually call the universe, is isolated. After all, by definition, the universe simply contains, along with the system, that part of the things around it which are all that it interacts with. So when you take the system and the surroundings together, whatever you get does not interact with anything else outside. So the entropy of the universe never decreases. In fact, it will stay equal only if d cross q by t's line integral for a closed path turned out to be 0, and that happens only if the entire process is reversible. So the entropy of the universe, not only does it never decrease, it actually always increases as long as the change that happens is irreversible. And as we argued earlier, almost everything that happens, and indeed everything that happens spontaneously, is actually an irreversible process. So the entropy of the universe always keeps on increasing. Now, since this is nothing but the statement of the second law in the entropic language, it stands to reason that all that we have talked about earlier as consequence of the second law or versions of the second law should be things that we can derive out of this particular version. Let's see whether that's true. Now, firstly, let's consider a situation where you have an anti-Kelvin Planck engine. Now, this anti-Kelvin Planck engine will actually take heat from a single reservoir And since it's going to take heat from a single reservoir, it's not an isolated system. However, the reservoir and the system taken together interacts with nothing else. The two together is an isolated system, something which we call the universe in this context. So if you have a positive Q which is going into the system, then the reservoir is losing negative Q amount of heat, and for a reservoir, the temperature T is always a constant, so entropy change of the reservoir is very easy to calculate. It's simply minus Q over capital T. As far as the system is concerned, it goes in a cycle. Therefore, entropy being a state function cannot change during the process. So if you add the two together, this minus Q by T for the reservoir and 0 for the system, you get the change in entropy of the universe is minus Q by T, something which is negative. And this is something which is impossible according to the entropic version of the second law. And thus, it tells us that an anti-Kelvin Planck engine simply cannot exist. Let us now take a look at the Clausius version of the second law. For this, let us consider an anti-Clausius engine. An engine which will take a positive amount of heat out of a reservoir at temperature T2 and supply it to a reservoir at temperature T1. So, the reservoir R1 at temperature T1 gains Q amount of energy and its entropy increase is simply plus Q by T1. The entropy increase for R2 on the other hand is minus Q by T2. This is negative. Of course, the entropy of R2 is decreasing because it's losing heat in this process. Once again, the system, the engine itself, does not have a change in entropy simply because it goes in a cycle, and entropy being a state function does not change for a cyclic process. The three taken together, the two reservoirs and the system, makes an isolated system or universe, and deltas of the universe is Q into 1 by T1 minus 1 by T2. Now note that Q is positive, T1 is actually bigger than T2, which means 1 by T1 is smaller than 1 by T2. This factor is negative, so we get a change in entropy of our universe as a negative quantity, which once again is impossible according to the entropy version of the second law. So the anti-Clausius engine cannot exist. Let me now show you how Carnot's theorem follows along the same lines. If you have a heat engine working between two reservoirs, then delta S R1 is losing Q plus amount of heat to the engine. So R1's change in entropy is minus Q plus by T1. R2's change in entropy is minus Q minus by T2. It's actually getting mod Q minus amount of heat, but it's losing minus Q minus amount of heat in the process. Of course, Q minus is negative, so delta S R2 is actually a positive quantity. And once again, the system itself goes in a cycle, so its change in entropy is 0. So the universe here, the two reservoirs and the system, which goes in a cycle, together has an entropy change which is given by minus Q plus by T1 minus Q minus by T2. This is greater than or equal to 0, and therefore we end up with the condition that Q plus by T1 plus Q minus by T2 has to be less than or equal to 0. This should be pretty familiar to all of you. This is exactly what the Clausius inequality would have given us. And we have already used the Clausius inequality in the last lecture to show that Carnot's theorem follows from this. So I'm not going to repeat that argument all over again, but you should realize that you could have derived the Carnot's theorems following these lines, starting from the entropy statement that the entropy of the universe can never decrease. Let me complete today's lecture by taking another look at the mathematical statement that we made about the second law. Note that we have already said this before. D cross Q reversible is not an exact differential, but it does have an integrating factor. This existence of the integrating factor and its identification as 1 over the absolute temperature essentially is a mathematical statement of the second law of thermodynamics. Now, the reason why this is a very important physics-based statement is the following. The moment you have 3 or more variables describing a function, then a differential involving 3 or more variables is not guaranteed to have an integrating factor. Note that there is a basic theorem in mathematics which tells us that any differential involving 2 variables, mxy dx plus n of xy dy, always has an integrating factor. That integrating factor may be difficult or simple to find out. Sometimes just inspection is enough. Sometimes you have to work very hard to find the integrating factor. But at least in 2 variables, you are guaranteed to have an integrating factor. The moment you have more than 2 variables, you are really not guaranteed to have an integrating factor. So the fact that d cross q reversible is not an exact differential but has an integrating factor is a statement which is not mathematically obvious at all. It's a statement about the nature of the physical world. And that is why this is a law of physics. Now, just to establish the statement that I made right now, that if you have more than 3 variables or even 3 variables, you may not have an integrating factor. Let me show you why you are not guaranteed to have an integrating factor if you have 3 variables, x, y and z. So, a differential omega of the form a1 xyz dx plus a2 xyz dy plus a3 xyz dz. The question that we are asking is this guaranteed to have an integrating factor or not? Now, just by taking our minds back to mechanics a bit, it's easy to see that this particular differential form can be written down in the form of a vector dot dr, and we all know that this is going to be exact if it follows a rule, or rather, if it is exact, the curl of the vector A has to be 0. Now, of course, if we start with any arbitrary a1, a2, a3, even if they are smooth differentiable functions, curl of a1i plus a2j plus a3k is not guaranteed to be 0. So, any differential written down like this may not be exact. However, the question is, does it have an integrating factor? That is, omega may not be exact, but if I multiply it by lambda, is the resulting product lambda times omega, where lambda is some function of x, y, z. Is that going to be an exact differential? Of course, if I multiply omega by lambda, the vector on this side gets multiplied by lambda. So what we are really asking is, can we find a lambda such that curl of lambda A is 0? Now, very simple vector analysis tells us that curl of a scalar lambda times a vector A is lambda, the scalar, times curl of A, plus grad lambda, gradient of lambda, cross A, and of course, curl of lambda A being equal to 0 means we want a lambda which satisfies this equation. Lambda curl of A plus grad lambda cross A is 0. Now, at this stage, lambda is an unknown function. A is a vector whose components are known to me. Question is, can I find a lambda such that grad lambda cross A will be negative of lambda curl of A? But note one thing. We definitely know one thing about grad lambda cross A. Irrespective of what lambda is, we know it has to be perpendicular to A. And since lambda curl of A has to be in the same direction as curl of A, this immediately tells us that if curl of A is not perpendicular to A, a solution to this equation simply is impossible. No matter what lambda you choose, this term will always turn out to be perpendicular to A, and this is in the direction of curl of A. If the two are not already in a this relation that curl of A is perpendicular to A, it will be impossible to find a lambda. And you can cook up plenty of examples of vectors where curl of A is non-zero and it's not perpendicular to A. And so there are plenty of differential forms which do not have an integrating factor. Note that we usually talk of our thermodynamic system as something which is described by a small number of variables. And typically we say things like pressure and volume may be enough to describe the state of a system. Or in other words, the differential d cross q would ultimately be a function of P and V dP plus another function of P and V dV. Now, if that had been a complete description of the system, then the second law of thermodynamics would have really been rather trivial, because any two-variable differential is guaranteed to have an integrating factor. However, you must realize that even for simple hydrostatic system, the state is actually never given by P and V alone. It's given by P, V and the number of moles N of the system. All three have to be stated together. Of course, we usually keep silent about N simply because N is held constant in most cases. But that is just for simplification. Even the simplest systems are usually described by three variables or more. And that is why the mathematics that we had just stated right now means that the fact that a d cross q reversible has an integrating factor is not a trivial mathematical fact. It's not something which follows just from the definition of a differential. There is a lot of other input which goes into this, and that of course is what makes the second law of thermodynamics a law of physics and not just an accident of mathematical fact. In the next lecture, we are going to take a look at several applications of the second law of thermodynamics. Bye till then.